Brad Urani. I'm a staff engineer at Procore. Thank you for that lovely introduction. This is a talk about data. Specifically, do you or do you not want to build your own data infrastructure, take control of your own data, build your own solution for collecting and piping and storing and reporting this data? The world of data is so replete with like cheesy quotes and case studies that I'm sure you've all seen stuff like this. With the power of big data, American Express can now identify 24% of accounts that will close within the next 4 months and reduce churn by 4%. Right? We all have heard things like this. Data are becoming the new raw material of business. I think this must be like a British person. Data are becoming the new raw materials of business. Information is the oil of the 21st century. This must be a Texan, right? Should I do a Texas accent? Information is the oil of the... Sorry, I won't do that. Big data is the secret to preventing hair loss and reigniting the spark in your marriage. I made that one up. It's not real. But of course, when we talk about data, we have to talk about what kind of data, right? Because we've got a million things we can measure. We're inundated with data, we've got monitoring and bug reporting data, Jira has data, GitHub has data. It's all over the place, and the key word in figuring out what we want to measure, what we want to report on is value. This is our word of the day, is value. Value is the key word here. We build software because it's useful. It provides value to the people who use it. Data is how we measure how much value we're delivering it, and analyzing it is one of the primary ways we can identify what to work on to bring additional value. As the lead developer, it is your job to make the best use of the resources at your disposal, and almost invariably, the most precious resource you have is the time of your developers. And if you don't know what your users want, and if we don't know what they're doing, okay, one more cheesy quote, the last one I promised. Without data, you're just another person with an opinion. So if you build features iteratively in an agile manner, you face a choice of what to work on almost every time you fire up your editor. Measuring engagement, what to focus on, what to instrument, how to interpret these numbers, how to drive your decision-making is a vast and complicated subject that everyone in the software development business, whether it's lead developers, executives, QAs, product managers, could benefit from studying. But before we get into all that, we have to collect the data and get it into the places we need it so that we can report on it. So we're talking about data infrastructure, of course. Woo! Yeah. I work at Procore. Procore makes construction management technology. We are based in Carpinteria, California, which is a beautiful little surf town in Southern California. And our second largest office is right here in Austin, Texas. And we make software for the construction industry. So if you're building a skyscraper or a shopping mall or a subway or an opera house, you're probably using our software to do this. Here's an example of what our iPad app looks like for drawing management and things like that. And when I joined many years ago, our data infrastructure looked kind of like this. We have an app, it's powered by a database, and all our analytics go to Google Analytics. Right? And I'm going to make a bet here. I'm willing to bet that some of you out there have data infrastructure that looks a lot like this. I see some nods. Yep. Possibly with like a bit of this, like just a little direct SQL on your production database. Right? Yeah, that's good. The reason I make that bet, and I know that, is because it has been the case of every single tech company I've ever worked at. And I've worked at half a dozen now, and when I joined, it always looked exactly like this. And honestly, this is not bad. This is perfectly fine. Google Analytics is a fantastic product. There is a treasure trove of data as you dig into it in there, right? In some cases, I think it is the best tool for the job. Things like inbound marketing attribution and ad spend optimization, things that is probably the best analytics tool, at least that I know of. But at some point, you may get to a point where it does not do everything you need, and you may have to make the decision of whether you want to build something yourself, build your own solution to collect and analyze this data. Brad's first law of data infrastructure, right, is if you don't need it, don't build it. If you have not unlocked all the value of what you have there, you do not need to embark down this path. If you're thinking of building an end-to-end data collection pipeline, warehousing, reporting solution, before you start, be very clear of exactly what your use cases are, what is the value it delivers, what will get you from your custom solution what can you get from your custom solution that you can't buy off the shelf, right? Because I know here everyone understands that software development is best done in agile ways with small units with incremental incremental delivery, you'd be surprised how many people forego their principles and decide to embark on building massive data infrastructure and way over-engineer and plan too big and go waterfall and lose sight of the core tenets that we all know make good software development, right? Maybe it's the lingo, big data, data warehouse, makes people think they have to undergo this massive planning session, when in fact data infrastructure can be delivered ticket at a time in an agile manner. So why would you need to build your own? Well, there are some shortcomings to using a third-party hosted solution, the Google Analytics and their various competitors in the world. It is immutable. Not the good kind of immutable, like immutable in programming languages or immutable infrastructure like Docker, like the bad kind of immutable, like you send off your data and you cannot change it. You oftentimes cannot delete things. You cannot update things, right? If you forgot to add additional fields, you cannot go back to add them. You cannot go back and attach user or account metadata. You're out of luck if someone changes their email address or their company name or renames a product or changes a UPC. You cannot split fields, combine fields, augment records from another database, or do a lot of these really, really valuable things if your data is locked up in someone else's solution. It cannot be joined. Chances are you have more than one source of really valuable data, perhaps in a CRM like Salesforce, in a marketing solution like Marketo or something, in a live chat system or other customer service platforms, NPS survey solutions, A/B testing platforms. When your data is all siloed in separate places, you cannot unlock the value that it can bring to you if you put it all together. And then there are laws and such, data sovereignty laws, security requirements, perhaps foisted on you by customers, government agencies, and regulatory bodies and the like, that may prevent you from using a third-party solution like that at all. Some people are very averse to client-side browser tracking and cookie tracking and things like that, so it may not even be an option to you. Little side note, deleting is hard. This is one of the things I learned when I started data engineering. It is very easy to collect data. Sometimes it is nearly impossible to delete it when it gets caught up in message brokers, multiple databases, buckets in S3. Tracking down all the places your data is hard. So if you have a requirement that someday you may have to delete someone's data, you need to be very, very careful how you plan and build these things and make sure that you can do that. And there's more, right? If you take control of your own data, you can use it to train machine learning models. You can drive custom UX experiences, right? You can give the data back to your customers and let them see a dashboard of their own usage. All very, very super valuable things. So if we decide we like all those things, we're going to embark on this journey. You've got your super team of superheroes, and you're all going to build these things. Does anyone have kids who watches this show, She-Ra? This is awesome. It's so awesome. My little 4-year-old watches this, and she goes to bed at night, and I just leave it on, and I continue to watch it. The plot is very complicated, but it's really, really cool. It's fantastic. So if you have this crack team of superheroes, right, developers, QAs, someone who knows Linux, a SQL wizard, and someone whose sole job is to spend all day writing IAM policies, because I swear that's the hardest part, then by all means, jump in and do this. So there's some things we need to know, though, once we get started. For instance, we have to choose some technologies. And this gets complicated, right? This is Matt Turek. He's a VC at First Mark, and they compile this every year. These are the tools you have to choose from, and they're immensely complicated and overlap in all kinds of weird and confusing ways. For instance, Apache Spark is the primary batch processing system, but it has a SQL interface, and some folks use it as a database, and it also has Spark streaming, but streaming is typically done by a dedicated streaming solution like Apache Kafka, but Kafka also has an embedded database and can do SQL on your stream, and your database, or your actual SQL database, can double as a batch processing system, and you may be able to stream changes from it. Whew. Also, they all have some kind of half-baked machine learning built in somewhere along the line, and good luck figuring out what is best for what, right? But I could say there are a few pieces that you will definitely run across that you definitely need to know a little bit about. The first one being streaming. Streaming is my favorite. So, what I'm talking about here when I talk about streaming are, oh, the stream. Ah, isn't it beautiful? We don't have streams like this in California. I mean, we do. There's just no water in them. Yeah. Also, the trees are like all on fire, right? Yeah. What I'm talking about are these kinds of things. The most popular is an open source project called Apache Kafka, which is fantastic. I love it. It's what we use. All of your major cloud providers have their own built-in streaming solution, which are mostly similar, but do have some differences. And to be quite honest, mostly very good. And the streaming solution can consist of anything from a few servers moving megabytes of data to massive cross-region installations with hundreds of servers moving terabytes of data. We pay for managed hosted from Heroku, and it's great. Other people are much more ambitious. Netflix is legendary. They have thousands of Kafka brokers and hundreds of engineers working on it, move trillions of messages and terabytes of stuff through Kafka. What these services do is they move data from one place to another. So you've got producers. These are applications that write records into the stream. They write it to what's called a topic. A topic is just sort of one sort of related group of data. It could be all your mobile app data or your web data or your user data or something like that. And on the other end, we have consumer applications that read it. And I'm mainly discussing Kafka here, but all the cloud-native ones basically work the same way as this. So back to our example app, right? We've got our app servers, we're serving browsers and web and phones, we're powered off this database. What you need is a way to reliably deliver it, to get it from that database into your downstream systems in a way that is fault tolerant, right? And high availability, so you don't miss things, and is non-blocking, so you don't block requests coming into your servers. And this is where the stream comes in very, very, very useful. Among its many superpowers, for one, is that it multiplexes. So what happens is when you put a message in a message broker, streams are sometimes called message brokers, right, or pub sub, event buses, all kind of the same thing. When you put a stream in here and it gets consumed, a solution like Kafka does not delete the message right away. A Kafka cluster has what's called a retention period. Ours is set at 2 weeks, where the message continues to stay on there, on disk, for 2 weeks. That means you can attach multiple consumers who all consume it, and they do not interfere with each other. Unlike other messaging systems like your RabbitMQs, right, or background workers like your sidekicks if you're a Rubyist, and those kind of things, the message stays in the stream, right? And so that way we can send it to more than one places. You may want to send it to some kind of third-party dashboard, like your mix panels or your amplitude, or even server-side Google Analytics if you want. Just because you have other things doesn't mean you want to get rid of that. You'll probably write it to your enterprise data warehouse. More on that in a minute. I'm going to talk about these. And likely you want to put it in some kind of permanent storage, your S3 bucket or your Azure storage or your Google Cloud storage or whatever you use, mainly just as a permanent backup, as peace of mind, mainly just because it's cheap, storage is cheap, and it's easy, and it provides peace of mind that it's out there somewhere, and you can always drop your database and recreate it. You might want to write something to a search index, and if you have it backed up in S3 or whatnot, you can always drop the search index and rebuild it, right? So Kafka gives us this multiplexing ability so we can write this data to all the downstream places we want. You could even call this your data lake, right? Which is literally, ours is literally an S3 bucket. It's your data lake if you want fancy, fancy buzzwords. But it also gives you the ability to replay. So once the data is in the stream and has this 2-week retention period, you can always replay it from the start of the stream. So if you make a mistake downstream and you did not capture all that data and you lost it somewhere, you can go back in time, replay it, and get your data back again. Some people even use permanent retention where they just keep adding disks to their cluster and they can go all the way back to the beginning of time always, replay it, rebuild all their downstream databases and all those things like that. It's very cool. And the other thing is a buffer. It acts as a buffer. I searched for cheesy clip art to represent a buffer. Like, what do you represent? What's a cheesy graphic that could be a buffer? And I couldn't think of one, so I just used a sword. I don't know why. It's She-Ra's sword, by the way, Princess of Power. Yeah. It buffers. What the buffer means is that the downstream solutions don't need to be working for you to write to the stream. If you're writing analytics out of a web app, and they go in the stream, all your stuff downstream can totally break, and it will. And it's all there collected in the stream, and when you get all your consumers back started again, it's there, and you didn't lose anything. So it works as an important buffer of your data coming out of whatever application or data source you're using. And we got some guarantees that go along with this. With all these data technologies, they all have semantics or guarantees, sort of the promises they keep. You may be familiar with ACID semantics from a database, right? Atomicity, consistency, isolation, durability. Streams and things have these semantics too, these sort of guarantees that they offer you. For instance, Kafka, my favorite, has this thing of at least once delivery. That means the way it works, the data is partitioned, and each partition is read in serial, and so that you may not bypass one message until you have confirmed until you have processed the one before it, right? And that way, if your consumer ever goes down, if it partially processes the message, or if you don't know if the message was processed, when you start it back up again, it will pick up where it's left off and make sure that you got that last message. So in that way, you can be sure with a streaming technology like this that you never skip a message, that you never lose data. And that is very, very, very valuable, and that is not true of certain other systems. Other systems have certain semantics. The other one it gives you is guaranteed ordering. And this is a little different too. This is different from, for instance, your message queues and various other technologies in that the order the records go in is the order that they come out. And that can be really, really important too. Imagine for a second you're writing data to a downstream database. And you have to say, send a sales receipt and a sales receipt line item. The receipt better come in first, and then the line item second, or you're probably going to violate some kind of foreign key constraint you have set up there or other thing. This becomes valuable when you're doing things like mobile push notification systems to make sure your users get the messages that they are supposed to get in the same order that they arrived in. And this is one of the guarantees that it gives you. Kafka is very, very powerful in that respect. So if you need those semantics, if you need those guarantees, being a good data engineer is about picking the solution that matches your use case and the semantics that you need. Caveats, right? I will tell you, running your own Kafka cluster is very hard. We don't do it, in fact. We pay for managed hosted, even though it's expensive. But a few other things that I wish I had known when I got started with this: not all tooling is created equal. Data engineering is not a place to be a programming language fanboy, right, or girl. Particularly if you're into PHP, JavaScript, or Ruby, the libraries may possibly not be as good as the ones that are sort of your your solution's sort of native language, which is Java for Kafka, Scala for Spark, Python for just about everything else. There's a bit of this, like, we discovered this the hard way. We used a very popular open source library to consume our Kafka. It's a Ruby library, and discovered that it was a little bit behind the times and that Kafka had changed, and we were dropping messages. We were having catastrophic offset fall, like the offsets were falling, and we were reconsuming entire partitions and reconsuming weeks worth of data because we were using an untrustworthy library. So this is kind of an area to be real careful what client libs you use, and you may have to use a programming language that is not your favorite to get the best, most reliable things. There's sort of this Tower of Babel going on in data infrastructure where you really do have to know a lot of programming languages and not be afraid to learn a new one to get it right. So, pillar number 2 here, the second little thing, the kind of major technology that if you're building your data infrastructure that you really need to learn at some point is the Cloud EDW, if you can't read that, Cloud Enterprise Data Warehouse. Honestly, I really got into data engineering because I love databases. They're like these boxes of algorithms and applied computer science, and you can dig in and look at logs and query plans and kind of see how they work. Actually, someone recently said, what is your favorite page on the entire internet? I'm such a nerd. I said it's the locking matrix on the PostgreSQL docs. I just look at that thing all day, and it's like my favorite. So come talk to me at the cocktail party if you want to chat about databases and stuff like that. What I'm talking about here are these kind of databases. These are hosted cloud databases, and they might be a little bit different than what you're used to. Amazon Redshift seems to be what everyone goes to if they're on AWS, even though it's an older design and showing its age. And then, of course, Azure, BigQuery all have their own really fantastic solutions. Snowflake, which we use as a third-party one that actually runs on Amazon or Azure, but is hosted and maintained by the Snowflake Corporation, and it's really great. These are cool databases that offer some really fantastic features. For instance, you can take instant snapshots. These cloud systems are backed by distributed file systems, kind of like a commit log in Git, a directed acyclic graph of file updates, and you can instantly create a snapshot just by having a pointer to a previous spot in the log, kind of like your Git commits, which is really cool. So you can have multi-terabyte databases and take a snapshot every minute and just have all your snapshots sitting there and go back in time whenever you want if you need them, right? Snowflake has a cool thing. It's separation of storage and compute. So you've got your data. It is actually backed by S3. But if different members of your team, different teams or different individuals are going to be using this data, you can assign them all different amounts of compute, and their queries will not interfere with each other, which is what happened in older databases, right? You can actually provision everyone their own compute nodes, and their queries will not cancel each other out or affect performance. Google BigQuery has training and querying of machine learning models built right into the database, and you can actually build machine learning models and query them using SQL. And they're so good, honestly, that they've started to supplant, in my opinion, batch processing systems. The third pillar of data infrastructure after streaming a database would probably be a batch processing system like Spark, which is a nightmare to set up and has a huge learning curve. And with a good database like that, honestly, there's more and more they can do and less need for that kind of thing. But I want to explain briefly something about how they work, because this is something that I found fascinating when I learned it. What makes these enterprise data warehouse databases a little different from like the Postgres's and MySQL's that you're used to is that these are column stores as opposed to row stores. So in your Postgres's and your MySQL's, right, the data is sort of laid out like this on disk. 1, Shira, Princess of Power, false. Do you see the theme here of my talk? It's, yeah. 2, Glimmer, Glimmer, Brightman. She's Shira's sidekick. She's pretty awesome, too. And that is actually the order that the bytes are laid out on disk, which makes it really efficient. For instance, if you want to fetch one row, all the bytes are right there, often on the same block or in contiguous blocks. If you want to write one row, you only need to write one block or contiguous blocks. But this is not how enterprise data warehouses work. They take that whole thing and they turn it 90 degrees. So now the 1, 2, 3 is next together. The names Shira, Glimmer, Catcher are together, etc. And they actually split this up into multiple files. They have a file per column, or they split it into multiple files per column, all with rich metadata so that if the data you want is not in that particular file, the database engine will not even open it because it already knows what's in the metadata and what's in there. What this gives you, also notice on the bottom, you can combine, we have two values next to each other, you can compress them, and in that way save scanning and storage. What this architecture allows is for fast aggregation. So if you're doing massive counts, massive sums over billions of rows, if you want to know how many people clicked a certain web page and you need to do massive aggregation queries, this is going to be the fastest architecture for you, and it's going to be able to deliver that much faster than a Postgres. Maybe not if it's tuned. I'll get to that in a second. But that's really sophisticated. What it is not good at is, for instance, fetching a single row, because that data is not all next to each other, right? Or writing a single row, it is very slow, and that is why you typically only batch load, right? And you could not use this, for instance, to power a web app, because if you only need to like select one row, the performance is awful. It's one of those classic trade-offs, right? It's big aggregations over individual rows is why you use these databases, and that's the main difference in how they work. Also, you don't need indexes. Now, I know what you're thinking. The plural of index is indices, but the Postgres docs say indexes, so I go with indexes, so don't look at me funny, all right? There are no indexes in these databases, and what that means is you can't get these like microsecond, response times for fetching things. But realize these other data, Postgres's and the MySQL's of the world, right? To tune it with the correct indexes, you need to know in advance what queries are going to be run, right? Which is usually because they're built into your application. That's how you know the queries are going to be running, and that's how you know what indexes to add. But that does not work if you don't know the queries that are coming. So if you have a reporting solution, you don't know what your users are going to ask for. You don't know what dashboards they're going to try to piece together, so you do not have the opportunity to tune them and add indexes you want. Enterprise data warehouses don't require indexes, and they're much better at that kind of flexible ad hoc thing where you really don't know what's coming. They are expensive. Just a warning. Most of them, I think this is actually kind of cool, most of them charge by the byte scanned, right? Sometimes you have to sign a contract up front, but the days of like tiered pricing and massive upfront costs of contracts are coming to the end. You pay per query in a lot of these, but be careful because that can get very, very expensive very fast. If you start running a whole bunch of queries, you can rack up bills pretty quickly. So, kind of the third pillar of data engineering, it's kind of the third sort of lesson that I learned doing all this that I really wish someone had told me beforehand because it would have saved me a lot of grief, is about quality control. That is making sure the data that you are giving to people is correct. And it turns out this requires a great bit of care. First of all, quality control is not the same as quality assurance, QA, right? QA is a role, often a person, maybe on your team. That's about testing software before it goes into production, testing before it's released. When I say QC, right, I'm talking about ongoing, continuous checking of data such that it will alert and flag you if something breaks, right? Data development is not like feature development. If you are developing a mobile app or a web app and it breaks and doesn't work, someone's going to complain. Someone's probably going to tell you, or they'll just stop using it, right? And eventually you're going to find out and you're going to fix it. With data development, if you make a mistake, it's that someone in your marketing department got the answer 0.2 and it should have been 0.3. And they just misallocated a bunch of funds or something like that. And there's a good chance that if the data is wrong, no one will ever know. So that means you must be the steward of the data that you send. Brad's second law of data infrastructure is that if it's not QC'd, it's wrong. And you should just assume it's wrong. We discovered this the hard way, back to my Kafka thing. We actually found out we were losing messages because we had misimplemented the consumers. And we didn't know that. It ran for months and months and months, and we collected all this data, and we were losing like 8 or 9% of the rows we were trying to write, which means that the reports that were being generated were wrong, and that's, as the lead developer, I took responsibility. That is my fault, because we made the assumption that Kafka docs say Kafka never loses message, unless you screw up the consumer, which is exactly what we did, and we didn't validate that it was working correctly. So make sure you validate what you're doing. Brad's corollary to Brad's second law is poop goes in, poop goes out. Mary told me not to curse, so that's why I'm not cursing. But whereas if the data goes in, it does not matter how good your downstream architecture is, your databases, your pipeline, and all that kind of stuff. If you're putting the bad data in, you get bad data out the other side. You are the gatekeeper. If a data mistake happens, despite your best efforts, despite your double and triple checking, despite your automated QC and manual QA, no one is to blame. But if it happens because you shipped something, because you put data in someone else's hands that you weren't 100% sure about, then you are to blame. As a data infrastructure engineer, you are the gatekeeper. You know the source and the pipeline. You and your team have the hunches, intuitions, and doubts. And you're the only one who truly knows where all these numbers came from, and you're the only one who can vouch that they're accurate. As lead developer, you need to make sure that everyone on your team is part of the QC, and everyone knows it is their sacred duty to only publish trustworthy data. No data is better than wrong data, I always say. I should have made a slide for that. That should have been Brad's third law. Yeah. Okay. Monitoring tools are a good start, right? Your StatsDs and your Grafanas and your Datadogs and stuff like that. Monitoring can make sure your integrations are running, right? They can make sure that the pipeline is functioning, but they can't really check the quality of the data very well. For that, you need to, once it lands in a database, right, run checks that look for duplicate records and report the counts in Slack or something like that. Look for new types of metrics that have arrived and make sure you're expecting them to arrive. Run queries automatically and report the results to Slack that show perhaps if there was a metric that used to be reporting and then one day it was gone and you're not getting it anymore, so you can get in there and investigate why, right? Look for spikes in certain events that, you know, above a certain number of standard deviations, you see a spike, get alerted so that you can figure out why that is. Otherwise, it's too easy for things to slip by that you didn't notice. A culture of checks and balances is what I like to say, and I think this extends beyond your immediate squad, because eventually these metrics are going to go, if you're a big enough company, they're going to go to someone in another department. I always like to make sure that they understand that they are stored in the database too, and the quality control process does not end with us, the implementers. It is the responsibility of the downstream analysts and business people and whomever else is consuming this data to also approach it a little bit skeptically and double check what they're seeing and make sure they understand where it came from too. A culture of checks and balances is required for your whole organization anytime you use data. It's great to instill a sense of shared ownership in this kind of thing, right, across your organization. Sometimes people hear all this, right, and all these like kind of quality control checks, and they revert to waterfall kind of things I've noticed. It seems like, but rather, don't let this happen to you. I believe that data solutions can be delivered in an iterative, agile fashion, that the best dashboard is the first one, which is literally just one metric and one SQL query on the other end. Do not let the need to do, like a lot of real thorough QC, let this turn into a waterfall process for you. That is not the goal. You've lost your way if that's what it becomes. Overall, I'd say I kind of boil down data engineering into sort of three principles. There's this culture of quality and shared responsibility, right? You've got fundamentals. You need to understand these solutions, not just how to connect them and start them and getting running, but what are the guarantees do they offer, right? Do they offer in-order delivery, right? Are they at least once, only once, or Or could they possibly skip messages? Different solutions have different promises, different guarantees, different semantics. And finally, the technology itself. You, of course, have to get it running, get it working, learn about the security protocols, learn how to set it up, learn how to monitor it, learn how to make it function. If you do all this, good question is, do you need experience on your team if you're going to undertake data engineering? Do you need someone who's done it before? Well, it will obviously help. I mean, it will definitely save you some grief. It will definitely save you some certain mistakes. But every day that goes by, these kind of cloud platforms make it a little bit easier. Every time there's another reInvent conference or something, all of these solutions make something that just makes it a little more approachable. And I would say that if you are brave and bold and know what you're doing and know what kind of value you are starting to deliver, that it is not out of reach for people who don't have experience with this kind of tech to jump right in and do it. A few books that I really like. Designing Data-Intensive Applications by Martin Kleppman is fantastic. It's high level, it's pretty abstract, but it's one of the best books I've ever read. It's fantastic. I really cannot rave enough about this book. Agile Data Warehouse. Agile, keyword, data warehouse, right, is a fantastic book if you decide to warehouse your own data. It's really, really wonderful. I'm Brad Urani. I work in Procore in California, and I've got a surprise announcement for you. For the first time ever, I get to announce that we are now hiring engineers in Austin. SRE, DevOps, mobile, web, security, machine learning, you name it. I'd love to chat with you if you're interested. Thank you very much.